Hello guys, welcome back to my channel. It's the Caribbean Bookworm, and if you're new here on this channel, we typically talk about bookish content as well as very occasionally science content, as we are doing in these past couple of videos. So if you like any of those two topics, feel free to immediately check out my channel through the little icon down below, and also feel free to hit the subscribe button and hit the bell notification in order to notify yourself of some more lovely content. Now, the superhero of The Flash is a very interesting comic book superhero that can tap into what is known as this mysterious thing called the Speed Force in order to make him run really fast and go through locations at what seems like almost at an instant. And recently, in about a week or less at the moment of the uploading of this video, there is a new Flash movie coming out. And before that, there were for a couple of years already a show on the CW about this same DC comic book character. Now, ignoring the issues with the main actor that's playing the protagonist aside, the movie is about Barry Allen, the Flash, basically wanting to use his abilities to travel back in time in order to save his mom and basically reunite with her in order to deal with his loss. And doing this and traveling back in time and changing things turns out to have repercussions as to events that happened in the main DC universe, or the movie universe that we know of. And with that anticipation in mind, there are some really cool concepts from The Flash, or from the movie version of The Flash especially, which I really wanted to look closer at, which alludes to some interesting real life concepts in physics, and some of them are very mind-bendy. So whereas I did this about 3 months ago for Ant-Man and the Wasp Quantum Mania to explore some topics in quantum physics, I'm going to use The Flash basically to explore some topics in what is known as the special theory of relativity. And that is basically alluding to how things would behave when you start to move at very high velocities that are very close to that of light. So what really motivated me to make this video is that when seeing one of the trailers for the Flash movie, I saw this scene where when Barry was kicking off to start running, everything around him seemed to be in this tunnel vision type of perception. And I thought that was so cool because that is very representative of what things would actually look like for something moving very close to the speed of light. So without further ado, let's explore that, as well as basically the super slowing effect which the Flash would experience as he's moving really fast. So he would see everything around him moving slowly. And lastly, we will also try to explore some ideas as to how time travel might come into play as well, at least hypothetically. So without further ado, let's start with that weird funky effect where you saw when Flash was running, and then build on from there. So in order to understand what is happening there and that really weird funhouse effect, let's look at something that's a bit more closer to home, that is a little bit more less abstract than something like the Flash. And that is, imagine if you were sitting right now in a train that is not moving, a train that is standing still, and there happens to be a thunderstorm outside and rain is falling vertically, basically downwards. If you were to follow a single raindrop in this instance, then say if there were 3 instances and you were to look at that same raindrop, at instance 1, the raindrop would be here, instance 2, it will be here, and instance 3, it will be there. So basically a vertical straight line. But however, if the train starts to move, and if this motion happens at a constant velocity relative to the outside, so relative to the ground, say if someone was standing outside of the train and seeing the train starting to move, then basically what you would perceive as for the raindrop that fell is this diagonal path basically that is tilted in the direction of the motion of the train. The reason for this is as the train starts to move, well, if you were to look at that raindrop and it being at instance 1, 2, and 3, well, if you're sitting inside of the train and if the train is moving at constant speed, then according to you, it won't feel like the train is moving. It will feel like everything on the outside is what is shifting away from you. And this makes sense. If you ever sat in a train or in a car as a passenger, and as that car is moving at a constant speed, then it seems like from that point of view of you sitting inside of the train or car, that it is everything around you that is going past you. So you see trees moving past you, you see people standing still from the outside moving past you, and you that is sitting inside of the car feels like everything is standing still. So with that in mind, as the train is moving, well, when you see the raindrop in instance 1, it might be there, and imagine you're sitting right now in the train and everything on the outside is moving. At instance 2, the raindrop would appear to be there as the whole ground basically is point of view has shifted a little bit. So the raindrop at instance 2 will be there, and at instance 3, the raindrop will be there. Hence why you get this diagonal line. Of course, if someone was standing outside and seeing the train move, then the raindrop will still appear to have fallen vertically, at instance 1 being here, instance 2 there, and instance 3 there. But of course, as the train moves, at instance 1, the raindrop is here. At instance 2, the raindrop is here, but the train has shifted a little bit. And at instance 3, the raindrop is here, and the train has shifted all the way. So that is interesting in showing you how basically points of view, or what are known as basically reference frames, so the frame at which you refer to things, how that plays a very key role. And the role that this plays here is the same with light rays, actually. So if you were the flash and you were situated right here, and let's say you were moving in this direction upwards, well, when you're standing still, there are light rays basically coming in from all directions towards you. But as the flash starts to move, all of these light rays will have a tilted effect, or what is known as an aberration, which is similar to the way rain basically tilts in the direction of the motion of the train. So if you were to imagine this being the train, it is moving forward, then basically the raindrop, instead of falling like this, will start to fall like this. So the same effect happens actually with light, as all of the light rays get squeezed a little bit more forward. This is a particularly funky effect known as light aberration or relativistic aberration. And for those of you who are a bit more technically inclined, I would highly recommend you to check out this book by Lightman called Radiative Processes in Astrophysics, as one of the things which he tackles is in chapter 10, basically this effect of light aberration, but of course in a little bit more technical detail. But for all conceptual purposes, basically this effect is the same as that raindrop effect, and what you're gonna get is basically the things that are in your peripheral vision, so not directly in your line of sight, while those things, light rays, are gonna be tilted somewhat, so you're gonna see things that are a bit more in your peripheral vision more in the front of you. And the things that are directly in the front of you are gonna take, of course, a little bit more time to reach your eyes compared to the thing that was a little bit more off tilted to you. For that reason, and I'm going to use a simulation of a game created by MIT to show this, which will show a really good example of how things would look like as you move closer to the speed of light. For that reason, you get that effect at which basically the things that are around you kind of seem a bit more forward in your line of sight, and the things that are well, directly in front of you, well, those seems to have been pushed a bit further away, as basically all of the light rays start to kind of converge forward. So it's going to take a little bit more time for that thing's light to traverse to you. But paradoxically, one thing which is important to note with things that are moving very close to the speed of light is that they experience two very interesting phenomena, and that is time dilation and length contraction. Time dilation is basically the effect at which if you have something moving really fast from point A to point B, then that thing moving really fast from the person, let's say if this is a train and the train is moving at like about half the speed of light or something, then if you were standing outside and seeing this train whizzing by, and say you measured that this train, in order to go from point A to point B, the train needs to travel like 500,000 kilometers. If you were to have like a really accurate binocular at which you can look at exactly what's happening inside the train, and you're looking at like an observer sitting in the train and like the train's apparatus at which it measures the distance which it traverses, then if you were to be somehow magically aware of the thing that the train is measuring, then you'd see something a bit more paradoxical, in that basically from your point of view, the train needs to travel like about 500,000 kilometers or something, but the train itself measures a distance that is much shorter than what you've measured it to have needed to travel. So what gives? What's happening there? What's happening there is because of the fact that the speed of light is finite, which in and of itself is a very interesting and funky concept and implies a lot of things. Because of the finite, you could say, speed of light, and the fact that everything in the universe is obeyed basically to travel either at the speed of light or less than the speed of light, then you get very interesting things and effects with time and space itself. And for a thing that is moving very fast, this means basically that the distance it perceives that it needs to travel is kind of squished basically. So according to the person inside of the really fast moving train, it doesn't need to move as far. And this kind of explains things with the Flash as well, as the Flash is running basically towards these great locations at very fast speeds. What he actually experiences is that the distances which he needs to traverse is actually much shorter, and this is experienced by the Flash by the fact that he can get from point A to point B much quicker than what someone on the outside basically would see him do. As according to the Flash, it doesn't take as long basically to go from point A to point B, again in contrast to someone standing on the outside. And this might seem a bit counterintuitive and paradoxical to the effect which we've just described with light aberration, as basically the Flash starts to kick off to run. Things seem to be a bit more stretched out, and you might have seen that with the simulation of the game as well. The reason for this is that basically the distance in between the thing that is going really fast and the endpoint which it needs to reach is actually squished. It does get shorter, but the effect with light is still the same. So the effect with the light aberration, with the light rays basically coming more towards the line of sight of the thing that is moving very fast, well, that is definitely still the same. And you still get that effect that the photons which are a bit more closer reaches the observer's eyes faster than the photons which are directly in front of him. And this effect, you can imagine, gets worse and worse the closer someone is running to the speed of light. As a matter of fact, I think it was in the Snyder cut of the DC movie, so small spoiler if you haven't seen the Snyder cut of the Justice League, when the Flash is running so fast that he needs to travel back in time, you can see, I think at one point, everything squished together in this really small white dot. If the attention to detail was there or not initially, and if this was the original purpose, doesn't matter. But basically, as the Flash runs super close to the speed of light, this effect of light aberration becomes so extreme that it seems like the place which he needs to reach is all concentrated at one really small finite point, and everything around him is basically dark. But he can reach this point at basically what seems like an instant to him. So it's a very trippy effect, but basically, even though distances will appear shorter to the Flash, the light coming off of things will appear to be infinitely stretched out. It's super cool. Now, besides the length contraction effect, there's also time dilation, and that is basically if, again, you have the scenario at which you have a really fast moving train and someone standing on the outside, and if that train is going from point A to point B, if, again, you had a magical way of viewing what's happening inside that really fast train, you'd see if, for example, the person sitting in the train had a clock, you'd see the rate at which the clock for the person inside of the train is ticking. You'd see that to be much, much slower than your clock as it is ticking for you standing outside. So if your clock for you standing outside ticks as the following, tick, tock, what you'd see happening inside of that really fast moving train might be something that is much, much slower, like tick, tock, tick. But of course, you'd see that thing happening at a much more slower rate, but you get the idea basically. That effect is called time dilation, and it is a very interesting effect, and it also explains why when Barry Allen is moving really fast, why he sees everything around him to be so slow. As you can imagine basically that if you were the Flash or the person standing inside of the train moving really fast, time still clicks at the same regular rate for you. Like it still clicks as tick, tock, tick, tock. And you'd see basically everything around you basically to experience a time that runs much slower. So basically you can imagine if you ask, well, whose distance is getting shorter or whose time is running slower? You can imagine the answer to be yes, basically. It goes both ways as long as both of these things are moving with the constant velocity relative to each other. In that case, well, both of them's clocks are running slower, etc., etc. So in the case of the Flash, as he's running, he sees the world around him to run at a much slower pace, and that's why when he moves around and he needs to punch people and such, it seems as if the whole world around him is a bit slower. And of course, that might seem a bit more intuitive to you in this context, as you might have seen a lot of superhero movies where you have Quicksilver, or maybe even in the Flash TV show, where they move really fast and everything around them slows down. But oftentimes, especially in, for example, the Flash TV show, it is basically explained as if because of Barry Allen's superhuman perception, he can see things in slow motion. Kind of like the analogy with athletes who are really in the zone, basically, can kind of experience things to be like in the moment, you could say, and in this kind of like an athlete's focused state that they don't notice anything else around them. They're completely zoned in. But what makes basically this concept stand on its own is that it isn't a perception thing, that it isn't a physiological thing happening with the Flash. It is a purely physical thing. Like, it is a legitimate physics fact. Like, everything around him does appear to be genuinely going slower, and it is less so of a kind of mental or processing thing, which makes it really cool. And it's how he experiences this slow motion type of thing when he's tapping into the Speed Force. Now, the last little bit of cherry pie that I wanted to explore is the notion of time travel. And this is one that is very interesting, but also very speculative. So everything that is going to be discussed here, take it with a grain of salt, or double check it if you want to. But I am going to state it as best as I can with legitimate physics concepts. So basically, if you were to look mathematically at how basically this time dilation thing is expressed as, and it is the only equation which I think I will use for this video, then it is expressed as the following. The time which basically the Flash sees his time click at. So if the Flash was wearing a clock on his wrist or something, then his clock would just tick regularly, like tick tock, tick tock, as the rate at which time passes around him seems to slow down. Well, basically, the way in which you can translate the Flash time to the time from the outside is by this following equation known as the time dilation equation, which tells you basically how much slower someone that is in that basically point of view that is not running as fast as the Flash, how slow basically they see the Flash clock run at. With that equation, you can express basically the time dilation, and in that equation, there's a particular thing in the denominator of this fraction, which is the square root of 1 minus the velocity, basically the velocity which the Flash has divided by the speed of light, and that being squared. Now, if the Flash runs at the speed of light is denoted with a c. If he runs at the speed called c, then basically the square root thing becomes a 0, and that's kind of a problem because you get a 1 divided by a square root of 0, 1 divided by 0. Well, mathematically that shouldn't be allowed. It's an undefined thing. Or you could say basically that it takes an infinite amount of time basically, or they'd see basically that it takes Barry Allen's clock an infinite amount of time to have one tick. So basically it would appear as if time doesn't even pass for the Flash. So that's already kind of very interesting and weird, and there are many reasons why it isn't allowed for things with mass, at least, to be able to go at these very high, at the speed of light, and only light basically, or things without mass, can travel at the speed of light. But without going too much into that, what happens if, for some hypothetical reason, the Flash was able to go at the speed of light and even beyond that? If the Flash goes beyond the speed of light, simply looking again at the time dilation equation, then you get the square root of a negative number, because you'd have 1 minus something that is greater than 1c, so 1 times the speed of light. So you'd have 1 minus a number that is bigger than 1, and that's going to be the square root of a negative number. Now, if all you've heard in mathematics were up to some high school algebra or something, you'd say immediately again, impossible. In mathematics, however, there are some things called imaginary numbers, which basically are just defined to be the square root of negative numbers. That sounds like hand smuggling and just throwing mathematical things out there, but these imaginary numbers happen to have a lot of use, such as in some things in electricity and in especially quantum mechanics. But however, this is still a very weird notion, as you're talking about time intervals here. And And these imaginary numbers, for one reason or another, which would take a little bit of time to explain, they are not the same as real numbers, which are things which we can kind of define, things we measure at in the real world with. So if these numbers which you get are so-called imaginary numbers for your time intervals, what does that mean? And one of the interpretations for this is that basically, if you have imaginary time intervals, it means basically that if someone looks at the flash, they would see him actually going backwards in time. So instead of his clock ticking tick tock, they would see his clock running backwards. So that's the whole idea that a lot of times these science fiction concepts take and run with, of basically something going really, really fast, and because of that fast motion, they go backwards in time. They even use this for the really old Superman movie, where he went basically really fast around the earth, and doing so, he was able to go backwards in time. But with the Flash, it's really cool, as it is very explicitly stated that this is kind of what they want to go with. But of course, this is very hypothetical, and physically there are no reasons up to this moment that basically time travel is allowed in this fashion. In this purely like special case of this theory which I'm talking about, nothing should be able to, nothing with mass at least, shouldn't be able to firstly reach the speed of light, and then secondly go beyond that. The speed of light being like the finite speed which anything can go at is very profound and has a lot of things to do with cause and effect and very, very profound things in the universe. But hypothetically, it is still fun to imagine what would happen in such a case. One of the hypothetical, you could say, things which physicists came up with, which would theoretically be able to move so fast, is something called a tachyon particle. And I will allude basically to a video made by Science Click English in order to look more into this, and also in order to look at just in general what it would be like to go closer to the speed of light. He goes into a lot more technical, well, not too much technical detail, but a bit more precise basically as to what would exactly happen, as of course he's someone that has done physics for a much longer time, so he would be able to give you a nice clearer answer. But tachyon particles are these hypothetical particles, or an exotic type of matter basically, which is predicted basically to be able to exceed the speed of light somehow, and basically have this going backwards in time type of thing happening. Another thing with time travel is that some theories in physics allow the possibility of some type of time travel through the way at which basically space-time itself is described, especially space-time when you have like curvature, very massive stuff, the type of thing you think of when thinking about black holes and things like that. But again, that is an entirely different story, and also it has its own set of problems. But I hope to have captured your imagination with some of these things, and also these notions of time dilation, length contraction, and light aberration, like you saw with the Flash, aren't just purely like speculative things which physics just think about for the fun of it. These are actually relevant things, especially in doing scientific research. For example, the effect of light aberration, which we talked about, is something that is actually taken into account for astronomers a lot of times, as when they look at galaxies, collections of stars basically, very similar to our Milky Way, but galaxies that are very, very far away. Some of these galaxies contain supermassive black holes at the center of them that kind of gravitationally bound all of the stars and gases. And astronomers look at these plasmas and just look basically at the light that is coming from them. Sometimes it seems as if these jets basically coming from the black holes seems to move at speeds higher than the speed of light, which seems very weird with the theory that is firmly established. So physicists looked at this closer and found out that this light aberration effect plays a very important role there. And same goes for the time dilation and length contraction, as that explains a really cool thing. For example, that in some scientific observatories where they try to measure basically radiation that comes from space, as we're constantly bombarded with high energy particles, really, really small things that you can't even see, but that are passing through us every single moment. In some of the observatories, they look for what is known as a muon, a very small particle, very analogous to like an electron or something like that. Problem with this is that the observatories, well, they detect these particles, and That's problematic because these particles have a very short, you could say, lifetime. Like they're supposed to decay in about 2.2 microseconds, which if you use your classical high school physics, where the distance of something or the distance that something traverses is equal to the velocity times the time, basically, even if these really small particles were moving very, very close to the speed of light, according to the classical equation, which you can have right there, they can only get so far through our atmosphere, and our atmosphere is very high. So according to at least classical physics, a lot of these muons aren't even supposed to make it all the way through our atmosphere, let alone actually the vast distances which they've traveled. So so according to our classical notions of physics, a lot of these muons aren't supposed to make it all the way through our atmosphere. And the reason why we don't even think about like whether or not they needed to traverse all the way through space is because it usually happens in this kind of a shower effect where you have a high energy particle bumping into one of the molecules in our upper atmosphere, and that bumping basically just that particle decaying itself into smaller and smaller particles. Well, the decay process, it's what produces this muon. So that can get a bit trippy in and of itself, but let's just run with it. This muon basically isn't supposed to reach the earth due to its very short lifetime. So how are scientists able to still measure this muon? The reason for this is literally this funky effect of time dilation and length contraction. Because these muons are moving so fast, we on the earth will see the time basically of that muon ticking much slower. So even though from the muon's point of view, it only survives about 2.2 microseconds, for us, because the muon is moving so fast, that might seem like a much longer time span, like something like 60 seconds, for example, or something like that. So it takes longer, meaning it traverses a larger distance, and meaning that, oh, there's a good chance that it might indeed reach the surface of the earth. And another thing is then, well, what about the distance, the height? For example, if the muon survives for 2.2 microseconds, then how can it traverse just a really short distance, according to his point of view, but still reach the surface of the earth? That is because of the length contraction. From the point of view of the muon, similar to with the flash, because it is moving so fast, basically the distance which it needs to reach seems a bit more contracted, seems shorter. So it reaches that destination much quicker, a destination which for us might appear to be a greater distance. And that basically in general explains how basically physicists are able to detect these muons despite their very short lifetime. So those are some really cool applications of this funky like model of physics in real life. So I hope I give you something to work with and captured your imagination a little bit, and also have got you thinking a little bit more deeply about the Flash. So I hope to see you guys soon, and I hope you enjoy your day and beginning of the week in general. Cheers and bye.